In this video, we're going to talk about a topic very closely related to quantum numbers and atomic orbitals. And that topic is electron configurations. So since we specify in an electron configuration which of the atomic orbitals are going to be occupied by electrons for different atoms. So electrons in many electron atoms occupy orbitals that are very similar to those in hydrogen. And we'll use the same quantum numbers and labels to describe them. So we'll still have S, P, D, F. The big difference between hydrogen and atoms that have more than one electron is that in hydrogen, actually the energy of the orbitals only depends on the principal quantum number. So 3s, 3p, and 3d orbitals in hydrogen actually all have the same energy. And so the orbital energy diagrams that we've been drawing to this point have actually been for many electron atoms. Because in many electron atoms, the energies of the orbitals depend on n and l. So in the n is equal to 3 shell, for example, the 3s orbitals are the lowest in energy, the 3p are in the middle, and the 3d are the highest of those different subshells. So up until this point, we've talked about 3 quantum numbers to describe an electron in an atom. N, L, M sub L, and it turns out there's a fourth that we abbreviate with M sub S, and it is the electron spin quantum number. And so electron spin is an intrinsic magnetic moment of an electron. This determines how electrons behave in magnetic fields. And it turns out there are 2 possibilities for this electron spin quantum number. It can either have a value of plus a half or minus a half. When it's plus a half, sometimes we call that spin up or alpha. And when M sub S is minus a half, we sometimes call that spin down or beta. Now, one common misconception about the behavior of electrons in an atom comes from the names that we use for orbitals and electron spin. So this can sometimes give the impression that electrons are like planets orbiting around the sun in circular or elliptical orbits, and then the electrons are sort of rotating on their axis like planets. And that's simply not the case. We know that orbits is not a correct description. Instead, electrons reside in regions of space that we call orbitals, and they're certainly not circular, and the electrons don't move in regular paths. And similarly, even though we use the word spin, the electrons are not in fact spinning. The electron spin just tells us how the electrons behave in a magnetic field. It has nothing to do with spinning electrons. And so, when we specify electron configurations, we're stating what orbitals are occupied by electrons for that atom. And so, to write down an electron configuration, there are 3 things that we need to keep in mind. And you don't need to remember the names of these principles, even though I've given them here. So the first is the Aufbau principle. And this just tells us that the electrons fill the lowest energy orbitals possible. But they all can't go into the 1s orbital because of the other 2 principles. So the second one is the Pauli principle. And this tells us that an orbital can have no more than 2 electrons. And if there are 2 electrons in an orbital, they're going to have opposite spins. So one's going to be spin up with a spin of plus a half, and the other one's going to be spin down with M sub S of minus a half. So the electrons want to be in the lowest possible energy orbitals, but I can only put 2 electrons in each orbital. And then finally we have Hund's rule. So when orbitals are degenerate, that just means that they have the same energy. Each orbital gets 1 electron before any gets 2. And when we put the electrons in, the unpaired electrons will have the same spin. And we'll definitely look at some examples of these electron configurations. So another thing that we need to be aware of is the ordering of the energy of the orbitals is not necessarily what we would always expect. So it starts off pretty regular. So the lowest energy is the 1s, then we go into the n is equal to 2 shell, and we have the 2s and the 2p's, and then we go into the n is equal to 3 shell, and we have the 3s and the 3p, but now you can see the first difference. The 4s energy is actually lower in energy than the 3d subshell. And that's in part due to the fact that the orbitals get very close together. And so you may be asking, well, how do we know what the ordering is? And it turns out the periodic table tells us exactly what the ordering of the orbitals is in terms of energy. So this is just an example of an orbital energy diagram. Last time I left off the n is equal to 4 subshell, but you can see, this is what we'd drawn before, and you can see the 4s is actually slightly lower in energy than the 3d, and then the 4p's are actually higher in energy than the 3d's. So the way we can determine the ordering of the energy of the orbitals is, previously I talked about this being the S block, and this being the P block, and this being the D block, and this being the F block. And the principal quantum number is given by the row in the periodic table. So hydrogen and helium, right, the helium, for this purpose, it would be easier if it was over here. We put it with the other noble gases because it behaves like the noble gases. But we first fill up the 1s, right, and then we're done, and then we come down here. Now we're in n is equal to 2, so then we have the 2s and the 2p's, and then now the 3s and the 3p's. And now we're in n is equal to 4, and so this is the s block, so what comes after the 3p's is the 4s. And then now we're in the d block. And so the only thing we have to remember is the principal quantum number for the d's is 1 less than the row they're in. So even though I'm in the 4th row, these are the 3d's. Let's use a different color for that. These are the 3d's. Right, and then we're back to the 4p's, and then the 5s. The first row is the 3d's, so these are the 4d's. So then we have the 5p's, the 6s, and then now we start the lanthanides. And so they're actually 2 less than the row they're in. So even though I'm in n is equal to 6, these are actually the 4f's. So we have the 4f's, and then I have the 3d's, the 4d's, now the 5d's, then the 6p's, then we have 7s, then 4f, 6d, and 7p. And so the periodic table tells me exactly what the ordering of the orbitals is when I'm filling them up. So sometimes you'll see a diagram like this to tell us what the ordering is. I want to encourage you, don't do this. This is not the way to do it. Use the periodic table. The periodic table is so much easier and so much more convenient than trying to draw this little diagram, and it's too easy to make mistakes when you're sort of setting these things up. So I know that this is what my high school chemistry teacher showed me, and I wish she hadn't. She should have just gone to the periodic table and not done this little diagram, because you'll always have the periodic table available to you, so you should learn to use the periodic table for predicting the ordering of the energies of the orbitals. Alright, so let's write some electron configurations. So, again, we can use the periodic table to do this. So, if I want to write the electron configuration for fluorine, I would locate fluorine on the periodic table, and then all of the subshells are full until we get to fluorine. So again, remember, we have, right, helium should be here, and sometimes so we have the 1s, the 2s, and the 2p's. And so I can put 2 electrons in the 1s orbital. I can put 2 electrons in any orbital. And so we would say that the 1s orbital has 2 electrons. And then, so we filled up the 1s. Now we're in the 2s. And we haven't got to fluorine yet, so the 2s are full. So then it would be 2s2. And when we're writing electron configurations, we just lump all of the degenerate orbitals together. Right? If we were going to look at the orbital energy diagram for fluorine, we would have the 1s, the 2s, and the 2p's. And so the 1s are filled. And so when I put in the arrows, for the one that has spin up, I drew an arrow with a half head up and another one with a half head down. So I have 2 electrons in the 1s. I have 2 electrons in the 2s. And then based on the column that fluorine is in, I have 1, 2, 3, 4, 5 in the 2p's. And so to finish off the electron configuration, it would be 2p5. And I have another video on orbital energy diagrams, but just to finish off the orbital energy diagram for fluorine, when we put in the electrons, so the 2p orbitals are degenerate. So everybody gets 1 electron before any gets 2, and they go in with the spins paired. So when I put in my 5p electrons, I go 1, 2, 3. Now I can start pairing them up for 5. If you're a little bit confused about the orbital energy diagram, it's okay. I've got another video specifically devoted to drawing orbital energy diagrams, and here we're just going to focus on the electron configurations. All right, if I wanted to do chlorine, so chlorine, let's get a different color, is down here. Right, so all the electron configurations start the same way. And so in chlorine, the 2p's are filled, and so I can put 1, 2, 3, 4, 5, 6 electrons in the p orbitals. So for chlorine, it's going to start out 1s2, 2s2, 2p6, then we go to the 3s, and then chlorine's in the 3p's. So the 3s are filled, so it would be 3s2, and then 3p5. And so one thing that you may notice is the end of the electron configurations for fluorine and chlorine are very similar. They end in 2s2, 2p5, right? Or chlorine ends in 3s2, 3p5. And so the arrangement of the electrons is very similar in fluorine and chlorine. And we talked before about the fact that elements in the same column of the periodic table tend to have similar properties. And the reason is the arrangement of their electrons is similar. So the reason fluorine and chlorine have similar properties is because the arrangement of their outermost electrons is similar. All right, let's look at a couple more examples. All right, so now we want to do zirconium. And so we want to find zirconium. And so here it is. Right, and so all of the subshells are going to be filled until I get myself to zirconium. So I always start off with the 1s, and then the 2s, and then the 2p's, and then the 3s, 3p's. These are the 4s. Now I get to the D block, and so the D's are going to be 1 less than the row I'm in. So these are going to be the 3D's. Then back up to 4. These are 4P's, 5s, and then 4D's. And so I can put 2 electrons in an S. I can put 6 electrons in a P subshell, and I can put 10 electrons in a D subshell. And so everything's going to be full until I get to the 4Ds. So my electron configuration is going to be 1s2, 2s2, 2p6, 3s2, 3p6, then 4s2, 10 electrons in the Ds, then 4p6, finally 5s2 is full, and so now I'm in the 4Ds where zirconium is, and it's in the second column of the Ds, so it's then going to be 4d2. And that would be the electron configuration for zirconium. All right, we'll do one last example. We'll do lead. And so lead's down here. And so again, I'll start with the 1s, 2s, 2p, 3s, 3p, 4s, then the 3ds, 4p, 5s, then we're 1 less, the 4ds, back to the 5p's. Now we have the 6s. At this point, before we get to mercury, we're going to have to go to the lanthanides. And so these are going to be 2 less. So I'm in row 6. So these are the 4f's. Then I have 3d, 4d, so this is 5d. And then these are the 6p's. And lead is in the second column of the 6p's. So it's going to end up as 6p2. So writing out this complete electron configuration, it's going to be 1s2, so 3 P's, then the 4s. So I'm at the 6s, now the 4f, and I can put, there are 7 f orbitals, so I can put 14 electrons in that full f subshell, then finally 5d10, and then we'll finish it off with 6p2. And so that would be the electron configuration for lead. And you'll see this picture in your textbook, and it gives sort of the outer electron configuration for all of the elements. And one thing I wanted to point out is that when we get to the lanthanides and actinides and some of the transition metals, they may look a little bit weird, right? For example, here's 5s1 4d4. Or down here, uranium, right? It's got some electrons in the Ds where we wouldn't have expected those yet. And so in a later slide, we'll talk about why some of these exceptions exist. But I'll only ask you to know about 2 exceptions, and we'll talk about those 2 specific exceptions in the in that video specifically devoted to the exceptions. But I did want to point out that things can get weird as those orbitals get really close together. Sometimes they do things that we might not expect based on the simple rules that we've talked about. But I'll largely want you to assign the configurations using the simple rules that we've developed, and there are just 2 specific exceptions that I want you to know.